So welcome everyone to our weekly seminar, and today I'm glad to have Dr. Shi here. Dr. Shi is an associate scientist and NASA Goddard, and she works in the Goddard Climate and Radiation Laboratory. She got her PhD in atmospheric science from University of North Dakota. And her current research interest is retrieving and characterizing global aerosol properties and focus on quantifying heavy aerosol loading. She has experience in developing and evaluating satellite aerosol products and applying them in aerosol data assimilation. Okay, so I will turn over to Dr. Shi.
Thank you. Today, I'm going to talk about characterizing the smoke emitted from the extreme biomass burning events over the Indonesia in 2015 using satellite observations from the AERONET. So as we can see, here has lots of smoke coming from, there's emission sources, lots of fires. Oh, I forgot to mention, so this work is, I thank my teammate from Modus Dark Target Group. Also, I thank the support from AERONET groups and OMI groups too. We're going to talk about motivations. Why do we want to look at these events, particularly, and then methodology. I will start from the case study in September 22nd, 2015. Over this day, we can see there's lots of smoke and the cloud mixed. And we'll talk about the research algorithm, what I changed and why this works, and evaluation of the research product. Then once we have this research product, we're going to talk about the impacts of this research product on the new aerosol climatology, and also the influence of these new aerosols on the regional and radiative balance. So here, why do we care about it? We all know these extreme fires actually are really rare, right? They don't happen often. They don't have all over the globe. They only happen, every couple of years with the conditions right from meteorology. But although these events are very rare, they're very important, both regionally and globally. Let's look at this image. This is just a random image shot on world view from September over the Indonesia region. And we can see, first, the impression. There's haze everywhere. The smoke is hazy, so smoke is everywhere. Second, we see there's different type of smoke existing in this image. It's not very clear because the projector, but here, this very thick blob of smoke is actually yellowish. We can see it's very thick, it's yellow. It's different from here. Where also very thick smoke exists, but it's white. It's different. And the second thing we see is we can see a lot of structure of the smoke. We can see here some smoke coming from the source regions here. And there's lots of smoke with cloud. We have different structures. So we don't know if it's a smoke structure or it's cloud structure, right? There's mixed. And then what do we notice? There's lots of Modus detected hotspot, right, of fire counts. But they only comes near the coastal, which is outside of the very thick smoke region. That makes us wonder, what satellite actually sees and detects may not be representing of everything, because a lot of these smoke burning is from the peat burning, and the peat burning is very different from the open flaming burning, which means that peat burning is like here. Let's take a closer look. The peat burning is not high temperature. You don't see the flame coming out. It's actually burning month after month. It's slowly simming underneath ground in those peat layers. It could be meters underneath ground. So you don't see the thermal signature there, but it emits a large tons of smoke because of that. You see all these white smoke coming without any fire. That's peat burning. Now here, there's another different type of burning which we actually pretty familiar with, which is open flaming burning. And because of the burning is not complete, we see black carbon, brown carbons emitted. So in Indonesia region, the aerosol that's emitted from the fire is mixed, but dominated by the peat burning, which is white, scattering, different from the burning that we usually know in anywhere else that's a little bit more absorbing. So what's this burning actually has an impact on our society and the environment? The Indonesia government estimated 2.6 million hectares of land burned in the 5-month period, which is almost as big as Belgium. You can imagine how much is burned. And all the crops and like the palm oils and stuff burned. And then the World Bank estimated $16.1 billion loss, which is 1.9% of their entire country's GDP in 2015. Study has shown 69 million people have suffered from health effects with 10K excess deaths due to the short-term exposure of these aerosols. And then model also estimated 100K excess mortalities across Indonesia, Malaysia, and Singapore due to the long-term transported smoke across the entire Indonesia, Southeast Asia region. So these are all the effects regionally, but there's more. These type of burnings also have impacts on global. So the global fire emission database version 4 estimated according to the satellite-derived data that in 2015, this fire contributed about 5% of the global carbon emission in a normal year. That's actually quite a bit amount. So these burnings, although they're rare, they have impacts regionally, they have impacts globally. And satellite data is what a lot of other downstream research use to understand their impacts. And it doesn't matter if it's health impacts, visibility impacts, or other like economic estimation, loss estimation and stuff. So to be able to give them an accurate quantifying these aerosols, the satellite data, how we be able to retrieve these aerosols, the first step, and it's very important. It has large impacts in all these studies, downstream studies, especially in aerosol data simulation and aerosol modeling. And that's the reason I want to study this and see how satellite is doing, particularly MODIS, dark target algorithm. Here's my case study, September 22nd, 2015, over the Kalimantan Island. So this is the Kalimantan Island. This image is an RGB MODIS image, and we can see, again, we see sea land breeze happening, so all the smoke is being trapped inside the island. We see there's the smoke, at least we think it's smoke, right? Very bright smoke, very thick. And we also see these puffed cumulus clouds surrounding the coast. We see some clouds here, and we don't know how much is underneath the aerosol deck here. This little star is the AERONET site. This is the AERONET site, Palakaraja site. So that particular day, the AERONET site does not have AOD at 500 retrieval. So I thought it's because it's underneath the cloud. But after I talked with Tomac, who's from AERONET team, he told me that day actually because AOD at 500 is so high, they did not report. But A7 did report above 5. So which means that at 500, it could be 7, 8, and above. But the day before and after that day, actually AOD 500 has values, which is 5.15 and 6.7 at 4 to 6 UTC time. So we can see that that day, like the ground data actually confirms that there is a very thick smoke existing, right? So what about satellite? So here's OMI AI, ozone monitoring imager, UV aerosol index. This AI, which representing if there's absorbing aerosol exists in the UV, absorbing in the UV channels. When the AI value is very high, which is above 3, above 2 and 3, we will consider there's absorbing aerosol existing. Particularly, we call it smoke or dust. But for this region, right, Indonesia region, for this time period, there's no dust source. So we can see the strong signals here is definitely due to smoke, absorbing aerosol smoke. Okay, these dark stripes here is from the OMI anomaly. The instrument has the issue after 2008. But, well, I also want to point out these very high values all the way to 7 may or may not be just caused by the absorbing aerosol. We need to keep in mind that if there's absorbing aerosol layer existing and there's a cloud deck underneath, it also triggers very, very high AI values. But nevertheless, both ground-based data and the OMI AI had identified that this region has very strong absorbing aerosol exists, right? Now let's look at MODIS, how MODIS, dark target and deep blue, two different aerosol products had retrieved over the scene. First of all, let's look at operational collection 6 image AOD dark target. So this is image AOD, which means all the retrievals is here. We didn't do any of the QA filtering. And then we can see it retrieves at low, quote unquote low, relatively low, right? It's actually 0.81, which is considered very high over the rest of the globe. But here, we call it low regions. Low regions here, right? And then you can see the increasing of AOD towards the center here, but for the center of the plume, there's no retrievals. It's too high, we cannot do it. And there's two other regions that we don't have retrieval, which is here and here. If you look, it's actually, you can see the strikes of, smoke coming out of the source region. So there's a very large spatial variations of these smoke because they just come out of these smoke points. Same as here. So also these two regions missing probably due to the spatial variations. Now let's look at here. This is deep blue. What deep blue has retrieved is quote unquote at low region again and at very high region. But then the transition, there's none. And then we can see like in the center of the plume, everything is 3.4. So there's no dynamic range of AOD retrieve. It's all at a capped value of 3.4 because deep blue knows here some exist, but there's no ability to quantify exactly the range of the AOD over this region. So why does the dark target does not retrieve, right? We don't know. So I go through the algorithm, we look at it. There's two main reasons. One is because the inland water mask, which is basically the NDVI of 0.87, 0.66 micron, is the main filter that filter out this region. And then the second is the low cloud mask, which is the top of atmosphere reflectance at 460 nanometer, and the standard deviation of it will filter out these data. Let's look at one by one. Let's first look at the NDVI, which is the inland water mask. What is this inland water mask? This inland water mask is first designed to filter out snow and standing water on the ground. So for example, melting snow, swamp, snow will be filtered out by this mask value less than 0.1. However, this is actually an overall powerful mask that helps us to only pick up the conditions that's premium for retrieving aerosols, which means other than this water problem, we also will mask out the cloud edges, bright surfaces, such as semi-arid areas, or urban, when the aerosol type, the surface is bright and aerosol type is very thick, or here, very, very thick plumes. So when the plume is too thick, we cannot see the surface. So this inland water mask, which is aiming to actually filter out the surface, will have bias as well. So here we can see the original cutoff is 0.1, which is yellowish, and then from 0.01, so less than 0.01, I put all in this light aqua color. It's very hard to see. But this whole range of color, which exactly masks out this area where the thick smoke exists, is what NDVI inland water mask has masked out. So that's one problem. And next, let's look at the low cloud mask problem. Low cloud mask, as I said, uses the reflectance at the 460 nanometer. So short wavelengths, well, we see very bright. Visually, we cannot tell if it's cloud or smoke, right? But no matter what, the smoke particle is going to be much smaller than the cloud particle. So although the shorter wavelengths have trouble looking at it, long wavelengths will be able to separate them, because if the particle is too small, the long wavelengths will not see it or will not be able to identify cloud particles. So there's this product which is called Modis Cloud Product Effective Radius Failure Matrix. So this is a matrix utilizing 1.6, 2.1, and 3.7 microns, so 3 longer wavelengths. What it does is it will try to retrieve, to look to see if they can see the cloud particles. If all 3 failed, so none of them will find any cloud particles, this matrix will return 3 failures. So when all 3 fail, then we know that these particles are quite small, and then we can think that these are actually small particles, not cloud particles. And be very conservative, we combine all these 3 failure matrices and produce this not cloud matrix, which is marked in red. So if red exists, that means all these 3 failure matrices will not be able to see cloud particles. Instead, we think it's aerosol particles. Let's see what it marks out. It marks out most of the regions that actually has has smoke here, but there are some regions, these puffy cumulus regions, we all, you know, actually they all think it's clouds, so it's pretty good. Even those regions that we not sure, visually we cannot tell if it's a smoke or cloud, which is this center here, the masks think they can see cloud particles. So we don't trust it. We say, okay, maybe there's a cloud mixing the smoke. We just be safe and don't retrieve over this region. Now we see here it's also emptied out and here emptied out. That's because this mask only applied when the cloud top pressure is found. So if it's a very clear region, there's no cloud top pressure, this mask does not apply. So combined with the original MODIS collection 6 and our new cloud failure matrix, not cloud matrix, we would be able to retrieve back these throughout pixels that are being considered a cloud, but it's actually an aerosol. So here that we be able to increase our data coverage by changing these two different masks. Now we want to actually increase our accuracy to retrieve over this region. Because the aerosol AOD, aerosol optical depth is so high, aerosol model really have a big impact on how we retrieve it, right? A little bit difference in absorption will causing our AOD to change quite a bit. That's why we need a regional aerosol model that actually can better represent this aerosol type over this region for the peat burning. And this is what I did. I used AERONET inversion data from August to October 2015, including 5 different AERONET sites, GMB, Kuching, Palagraya, Pontiac, and Singapore. So for all these 5 sites, here's the aerosol size distribution and refractive index I got. Let's look at the size distribution first because it's very interesting. All these, I have been separate them in terms of AOD, so group them in AOD at 675. We can see from yellow, which is low AOD, to black, which is very high AOD. We see a very steady trend, a very large increase of the size distribution in the 5-mode aerosol model. You see so it could cause by the aggregation of the smoke, it could cause by the humidity, but nevertheless, we see this increase of 5-mode particle size in terms of AOD. And then let's look at the refractive index. Oh, by the way, this type of behavior is also reported by Tom and Jeff Reed as other. People have found it, but they haven't confirmed what is causing of it. There's still debate, but here we see this trend as well. Now let's look at the refractive index. First, let's look at the image part. Image part represents absorption. Very interestingly, most aerosols will have very high absorption at very short wavelengths, but this one doesn't because it's such a white smoke. It's very less absorbing than the rest of the aerosol smoke model that we know, right? And then most of them has very little difference between each other, you know, in terms of AOD. Let's look at the real part. The real part separates, especially when AOD is really high, but generally it's flat as well. Some people would argue, they would think that real part of refractive index from the AERONET inversion retrieval may not be the most accurate one because, you know, AERONET has its own uncertainties. However, by keeping all these 3 variables consistent as function of AOD, we would be able to have a conserved radiative balance on TOA and be able to use it to accurately represent aerosol models in our retrieval. Oh, I also want to mention that here I use AOD 675 only greater than 0.4, which is much more conservative than what the AERONET team has recommended. They recommended AOD of 440 greater than 0.4. For these conditions, 675 greater than 4 is almost double the AOD loading. So we have more signals. So now let me give a summary of what changed in this research algorithm. We did 3 different stuff on the operational target algorithm. The first part is increase the data coverage, which including turn the NDVI threshold from 0.1 to 0.01 to include heavy smoke. We did a boundary sensitivity study to try to truly understand NDVI's behavior over this region, and we found that when NDVI less than 0.02 is definitely water. And then between negative 0.02 to 0.01, it's kind of ambiguous, so we just try to be safe. But above 0.01 to 0.1 for this region is very safe to use this value. However, if we want to apply globally, then we're going to have some challenge. And then we also have using the combined dark target cloud mask with failure matrix from MODIS cloud product to recover the misidentified smoke. This is trying to use in the long wavelengths to identify difference between a cloud particle and an aerosol particle. In the end, we removed the upper AOD retrieval cap, which is equal to 5 in the operational algorithm. Now, I want to mention when we did this, you would imagine we will have an extrapolation of AOD, so it can go very high. However, MODIS does not have the sensitivity when AOD goes to too high. So when we do the quantify, when we want to quantify AODs and use it quantitatively, we want to keep the AOD less than 6. Some people suggest 7, but I say 6, which is much more safe. But here we do allow the AOD to go high. The second part is to increase the accuracy of our retrieval, which we changed the aerosol model from this operational model to research model. Let's look at the 3 parameters that we changed. The first is the particle size, the volume mean particle size. What we notice is this parameter in front of tau, which is AOD, had become pretty large, which means that we have a larger dependency of particle size on AOD. The second is the real part of refractive index. We didn't change much, actually. The imagined part of refractive index, we can see that this value in front of tau is much, much smaller because this is a not so absorbing aerosol smoke model compared to the rest. It's very scattering. Now I want to mention the third part, which is very important because this research algorithm is only meant and designed to retrieve aerosols over granules. MODIS granules actually has this heavy aerosol feature exist. We do not want to apply on any granules that does not have this feature. So we need to first go through a pre-select procedure to make sure that all the granules we feed in to this algorithm actually has this very thick smoke exist in the granule. That's why we did these 2 different criteria. One is the OMI UV aerosol index greater than 2. When it's greater than 2, we know there is a strong absorbing smoke exists in this granule, but we don't know if this smoke is actually underneath the cloud or at the edge of the cloud. So the second part is trying to get rid of these scenarios when the small amounts of absorbing aerosol above the cloud or near the edge of the cloud, which means that MODIS C6 AOD needs to greater than 2.5 for at least 5 pixels. This will ensure that at least the original algorithm that's very conservative also thinks that very high AOD exists in this granule, and it is not because of the artifacts caused by the cloud edge. So after we've applied these 2 criteria on all the MODIS granules from August to October over the Indonesia region, we found 80 granules to run the research algorithm on. Now let's look at what changed after we run this research algorithm. Here is the operational MODIS C6 image AOD, which I had showed before. This is what we get now. The first impression we get is now we have very smooth transstream from low AOD region all the way to the center of the plume. We have a lot more retrievals with dynamic range from 2.5 all the way above 5 here. Second, we realized that we have a lot more data retrieved over the regions near the source. Let's look at this. This is the research AOD minus stock target operational AOD. The green means where this previously has no retrieval, now we have retrieval, which is near the source region and at the center of the plume. And then the color blue and red, blue means that research AOD is lower, and then red means the research AOD is higher. We can see generally, dominantly, the research AOD has been lower over these regions. That's because we changed the model into a less absorbing aerosol model, and consequently, we have lower AODs in this region. Oh, yeah. So now let's look at the validation of our product. We use AERONET version 3 level 1.5 AOD. Collocation is 0.3 degrees spatially and 30 minutes temporally. This right-hand side, the x-axis is the ground truth AERONET AOD at 0.55 micron, and the y-axis is MODIS stock target AOD. The black dots is the operational AOD, and then the red dots is actually we only changed the aerosol model without changing the increase the data coverage. So what we see is the bias first is very high, 0.34, which means we have overestimation before. And now the mean bias, just by changing the aerosol model, goes to negative 0.04. And then there's 61 data total before, now became 71. Why? We didn't change it. We didn't change the data coverage. Why there's more data? Because previously there's lots of data above 5, or actually 10 data above 5. Now with us changing this aerosol model, these 10 points come back in without the retrievable range. And this part is the research AOD that has both the aerosol model change and the data coverage increase. Then we can see, first of all, we see it's quite a bit good on a one-to-one line. There's not too much of scattering, right? The mean bias 0.04 with 93 data. The Roomy square error is reduced as well. Now let's only compare the operational AOD with AOD greater than 1, and then the research AOD with AOD greater than 1. The Roomy square error is almost, a third. And then the number of data at high AOD regime is doubled. Let's look at it in a bias plot. This is MODIS AOD minus AERONET AOD as function of AERONET AOD, so bias as function of increasing AOD. The blue is dark dark AOD, and the red is research AOD. We see that before the one AOD is less than 1.0, it is almost similar. There's not too much change between the two products. But when AOD is greater than 1, the bias are almost cut in half from research AOD when compared to the operational dark dark AOD. So from this validation, we see that overall we increase the number of data at high AOD region, and we reduce the bias by half. Now, how is the data coverage increase in time-wise, right? So this is a time series of AERONET and MODIS from 240 to 300. This is like late August, early September, all the way to the end of October, where these 80 granules actually are happening. The gray is actually all the AERONET retrievals at 550. I mean, all means it doesn't matter. Like it's as long as AERONET has retrieval, we plot it here. And the blue is research. The blue is the operational AOD, and then the red is research AOD. We also plot every single pixel that's collocated as well. So if this is the AERONET site, every pixel that's within 0.3 degree and 30 minutes was plotted. So there's a line of spatial variation to represent AERONET's temporal variation. And we also see there's some little cross. What the cross is, these MODIS data is spatially collocated with AERONET, but not timely, because sometimes AERONET retrievals is too far away, like an hour apart from the MODIS passing time. But because this particular feature will linger in the area for days, so that's why within a day, if it is spatially collocated, we show it in a cross as well. We only plot two sites here, which is the Pragraya and the Pontiac. We see first, there's very little blue. Doesn't matter if it's cross or dots, which means previously the operational data has very small temporal coverage of this event. Now with red, we see it everywhere, and generally it has very similar magnitude as what AERONET. Actually surprised me is like here, the spatial variation of one MODIS catch actually can represent the temporal variation of the AERONET catch. Like we catch the peak pretty good with these patterns. Like. So now that we have this new product, we validated it. Let's look at how it influenced the change of the regional aerosol climatology. This is a spatial distribution of seasonal mean AOD from August to October in 0.5 degree resolution. This is the operational DT. This is the research AOD. And we clearly can see these two regions where the burning happening the most, right? It's the South Kalimantan and then the center of Sumatra Islands. And then in some of these regions, the difference actually goes above 3.5 and then 2 to 3. That's actually very significant amount of AOD change in terms of 3 months mean over these regions. It's huge. 2005, that event's only happening in 2005, the biggest event. So every 5-6 years, there's another big event happening, but this is very big. Yeah. So now let's look at how a number of AOD changes, like histogram change. So before the AOD cuts at 5, right? Now we have a lot more AOD Oh, this is in log normal scale too. So for AOD around 5, it's actually double the amount of AOD we get here. It's a lot more. There's a lot more data when AOD greater than 2 is happening, and then almost double when AOD is 5, and about 5. And then I calculate the monthly mean, the domain mean. So the domain means like the entire this region, right? The domain mean land, ocean, for C6 operational and then research product. The first thing we know, and then in different months too. So first thing we know, the ocean doesn't change, of course, because our algorithm only apply all over land. Only the coastal region, when you aggregate it in, you will change a little bit, but mostly ocean doesn't change. The land, August, there's almost no change because August, the burning hasn't really get so intense yet that we don't have too much change of AOD retrieval over this. But in September and October, the entire domain over land mean increased about 0.2. And again, that's climatology, why it's very significant. So now that we know these are the new aerosols that we have, how does it change our radiative balance, right? How does it change our heatings? How does it change our TOA balance and surface balance? That's why I use the Libradtran radiative transfer model to simulate the radiation budget using this research product. And the average calypso aerosol profile over land from September to October 2015 is used to represent the aerosol distribution vertically. And then the interpolated MODIS 8-day albedo products, the all-sky albedo, is used to represent the surface. Here's just a quick table to show what I used, the aerosol model from AERONET, vertical distribution calypso, solar metrics and then conditions, the standard for MODIS AOD product. This is from albedo product. I want to mention a little bit more about MODIS product, albedo product. This is the 8-day albedo. If there's instantaneous albedo that we can get, we use it. But throughout the September, October, there's many days, the smoke cover is so large, you just have no retrieval of surface. You just can't see the surface. What do? We use the clear days before and after the fire, and then we interpolate them in middle to represent the surface. So the input aerosol vertically 21 total layers from 0.3 to 6.3 kilometer every 0.3 kilometer, but outputting heating rate and stuff is every 1 kilometer from 0 to 5 kilometers. Oh, the solar shockwave flux is integrated from 257 to 4 micron with low trend aerosol molecular absorption. So here's what we get. This is the heating rate. This is the research product here, operational product here, 1 to 2 kilometer here, and 2 to 3 kilometer here. I choose these 2 layers because that's where most of the aerosol exists. We see first in October there's the little hole. That means over this region, this entire October we don't have retrievals. So here is what do we have? And if we average over these 2 domains where the burn happened the most, the heating rate is about 0.4 K per day instantaneously. So for this region, we're looking at a quarter to a third if we do a 24-hour average. So about 0.1 K per day increase in the temperature in the 2 to 3 kilometer. So if we look at the lapse rate, we see there's about most change happens in 2 to 3 kilometer. It's about 10 to 15% of differences in the lower atmosphere heating. And this is the shockwave flux, the TOA upward flux here, surface downward flux here. Again, we see a huge differences. And if we average them, we see TOA cooling increased 41.6 and 24.1 watts per meter square instantaneously. Again, that's about 10 and 6 watts per meter square in 24-hour average. And here the surface cooling increased 85 and 48 watts per meter square instantaneously. So, but how much we trust this value, right? It's modeled value. There's lots of uncertainties. I also conduct an uncertainty analysis. It includes general assumptions and model setup, which how much uncertainty is related to the line integration, the standard atmosphere profile, the gas absorption, aerosol attitude, and vertical distribution. So these are all considered and calculated, which is considered, the other change. Second, how much uncertainty is coming from aerosol model, because like I said, somewhere it's the peat burning white smoke, somewhere it's brown smoke. How much if we vary these aerosol model, how much it's gonna change. So we also calculate a general smoke model versus AERONET instantaneous aerosol model. So the general model is what we use, right? One model fits for all, and the AERONET instantaneous model is for each site they have instantaneous. So that's the aerosol model related uncertainties. And then the third is the surface albedo. How much is that changing? What we do is we change the different resolutions. We try to see the area without aerosol albedo provided, like how we use the interpolated model versus the instantaneous model, and calculate how much that will change. And that is also a function of surface type, because you have dark surface, you have cropland, and you have urban, right? So that's the albedo part. And then the tau part is what we use the research AOD versus the operational AOD. So here's just an example of the uncertainty, because that's way too complicated to talk now. So I'm just going to do one. So this is dark forest, group 1, hilly and cropland, group 2, urban, group 3. The variation of 0.5 degree resolution as function of AOD. And then we can see there's a different lines of uncertainty line that we get. Dark forest, of course, is very small, but then for hilly and urban land is pretty big. So this is just an example of how the albedo uncertainty is. And we find actually, first of all, if we use all instantaneous, the AERONET version 3 and series level 2 SSF product are all agreeing with what I calculated very, very well. 0.04% difference and 0.05% difference. That means if we can have instantaneous, albedo instantaneous aerosol model, we can get very good agreement. But if we use average aerosol model, then you're looking at, you're looking at this much, half of the uncertainties when AOD is equal to 2 is when I use the regional model. But the biggest uncertainty source is still the surface. The surface is 30 watts per meter square, and then 13 watts per meter square when AOD is really high. Okay, conclusions. An event-based research product is generated over Indonesia region, targeting the thick smoke plume during the burning season. This product is based on operational Modis DT algorithm and utilize OMI, AI, and Modis cloud products. A regional peat burning smoke model is generated with less absorption model as function of AOD. So the single scattering area is about 0.96 and 0.98, depends on your wavelength. The research product doubled the number of AOD with AOD greater than 1 compared with the DT AOD product, and the bias of the AOD is reduced to half for AOD greater than 1. The research product captures the elevated instantaneous AOD that AERONET observes and provide a more complete picture of aerosol loading over the 2015 Indonesia wildfire. These extra aerosols change the regional shockwave radiative balance. And there are regions where the instantaneous heating rate increased largely, and with increased TOA cooling and surface cooling. So this work, currently we try to extend it globally, and like we tried in Russia, and this works actually. And we tried in Beijing as well. So we want to do it. We want to expand it globally as well, as long as we have funding. Well, thank you. Questions?
Very interesting and comprehensive talk. So questions?
Nice talk. So question is, when you try to extend this, because your retrieval is very much based on kind of prior knowledge, either from AERONET on the ground or from the model. And if you try to extend to large scale, you have to find a way to determine what the single cell albedo will be or other type of aerosol mixture, because that can vary considerably. The aerosol single cell albedo for smoke really range very large and generally much smaller than you have. This is probably because the water vapor, high water vapor over that region making it larger. So when you apply to Russia, Beijing, or anywhere else, you have no idea what's the single cell albedo. How would you do that?
Oh, so actually very good question. That's our biggest problem to apply globally. So we have two different ways to deal with this. The first way is just brutal force way, which means we have AERONET everywhere. We're just trying to absorb AERONET and compare different peat burnings, like Alaska peat burning with Russia peat burning with Indonesia peat burning. So we will have a pattern, right? It can be a function of humidity and stuff like that. That's what we try to do. But we're not really happy with this approach. We tried it. It doesn't, like, it doesn't work that well. So me and Santiago actually wrote a proposal, and it got funded. What we're doing is right now we're going to try to retrieve the single scalar albedo instantaneously using the UV channel. So it's being applied on amps and virs. We're trying to, add the prior knowledge of single scalar albedo from the amps, and then come back use it in MODIS. So MODIS help with the AOD, and amps helps with the absorption. So that will actually really solve this problem in a good way, I think. But that project is just started.
Okay.
Continuing on the same point,
yeah.
If you look at the true color image you showed, you pointed in your first slide that part of the plume is yellow and part of the plume is white.
Yeah, yeah.
So you kind of like making the plume almost gassing and no absorption, so you probably see better sort of a plume where yellow.
Yeah, if there's a very strong brown plume, you will have a very low bias all of a sudden. Okay, Lorraine actually tried this project for PACE, for precursor for PACE. But because OMI has time differences with aqua, and then there's angle differences, they just don't have success. They're just not successful with it. But now we're using amps and virs, which is on the same one. It's much, it's almost looking at the same angle. We have seems like better luck to actually get it to help each other out, to help the algorithm. Footprint is different, so we need to use a very. Okay, so if it's original, like if it's operational amps, it's very large, 50 kilometers, but they have two different modes. They have research mode and final research mode, which gives me 10 kilometers and then 1 kilometer. So the 1 kilometer and 10 kilometer one we really could use to identify different patterns of smoke.
Yeah, nice talk. Did you compare your part, because actually for aerosol model here you mentioned the two things you need to change. One is the particle size, another is the reflective index. Did you compare your particle size against the NASA GOCA model, like a black carbon or the organic carbon? Okay.
That'll be interesting.
Second question is how you determine those reflective index. You reduce the reflective index.
The refractive index is from the inversion product from AERONET.
Okay, it's a retrieval.
Yeah, it's a retrieval. Yeah.
Okay.
Yeah, their absorption is quite accurate. They have uncertainty published, but the real part is.
Does the retrieve the reflective index depend on any assumption of the particle size? When you retrieve the
so they retrieve particle size first, and they use particle size to retrieve their refractive index.
Okay.
Their particle size, I mean, of course, because they need to fit in the model, so there is going to be uncertainties in the particle.
Yeah, probably if you can compare the GOCA model, it would be more interesting.
Sure,
Because you need to have a consistency.
The model, I think the model doesn't even really do well if this the model does very poorly in this region. After I have this product, I try to collaborate with some of the modelers to see what's the impact, but they can't even pull their model up to get enough aerosol over this region. So the aerosol properties is just the secondary problem for them. Like their AOD is not even high enough for this region. They need to multiply by 3 and 5 to get to that point because there's no emission. Like I said, peat burning doesn't have enough heat to trigger these hot spots. If there's no emission, the model can pull up the AOD. You have data simulation goes in, it pulls up once. The next time period, it drops down again. So they have huge trouble over this region at this moment. Yeah.
But there are two, like a community. One community, like which we call the remote sensing group. You have your own definition for the particle size or aerosol model, and another for the weather forecast or the air quality model. So, but however, you want to assimilate your profile.
Yep.
Then the particle size is not consistent.
Yeah, so what we can provide, what satellite can provide is not what the modeler wanted. So there's a gap, and yeah, and if you're interested in that topic, the AirSat AirCom, which is going to happen in next month, they have a specific session devoted to that. So it will be very interesting to you. They have been trying to work on this, but not too much progress yet, I think, for years now. Thank you. Thank you.